Okay, so let me just give you, let's just put the example into a more solid mathematical footing. All right. So let's just continue on this example and figure out what can we do to obtain a finite element approximation. So one thing I want to answer, maybe we have some confusion is that so far the finite element method still has nothing to do with differential equations, right? And just it's finite element method for just approximating a function. And you're going to see pretty soon that the method actually generalizes pretty easily to some differential equations. Not all differential equations, but some differential equations. Just like finite volume is not suitable for solving any differential equation, it's only suitable for solving conservation laws. That's for finite volume. Finite elements also are not equally designed to solve all differential equations. It is most naturally applicable to the kind of differential equations that can be formulated into an optimization problem, into a minimization problem, naturally. And what that means is going to be clear in a few minutes. But let's just first look at an optimization problem, a minimization problem that comes out of function approximation, and see how finite element method does the function approximation problem. All right, so the function approximation problem we are going to look at is actually a very easy one, a very simple one to start with. We have x, and we have a, let's say, a function of u of x, okay? And I have two elements from 0 to 1 and from 1 to 2, okay? And I have constrained myself to a continuous and piecewise linear function. So in this case, how many degrees of freedom do I have? Two elements?
3.
I have 3, right? So basically, my degrees of freedom is, let's just say u0 is equal to u at 0, u1 is equal to u at 1, and u2 is equal to u at 2. I just have these 3 degrees of freedoms, right? And let's say I want to approximate some function like that, f of x, as much as close as possible. So what does it mean? It means I want to minimize by choosing my u0, u1, and u2. By choosing these 3 numbers, the averaged squared discrepancy between f and u. Okay, mathematically, how do I write down the averaged squared discrepancy? Okay, so first of all, I want to write down the discrepancy. F of x minus u of x, right? That's the discrepancy. The squared discrepancy is the squared, okay? And what is the average of a function? The average of the function, just as we discussed in finite volume, right? We should be familiar with that already. It's the integral of the function over the entire domain from 0 to 2. And I just divide by 2, right? So that's minimizing the average discrepancy between f and u. All right. So who knows how to solve minimization problems like that? It's a scalar function of 3 variables, right? The 3 variables is u0, u1, u2. How do we minimize a function of 3 variables? Did anybody, did you study this in multivariate calculus? Hello?
Is it like matrices?
not really. It's a function minimization problem, right? So if you have a one dimension, if you have a function of one variable, so let's just take this, let's denote this as j of u0, u1, u2, right? So it's a three-dimensional, it's a function that has three inputs and one output. How do we minimize? How do we choose the inputs of the function to minimize the output? Okay, so they didn't teach you. Okay, I guess. So this is actually a generalization of what is natural in one dimensions. Let me just draw what happens in one. So if I have j just as a function of u0, okay, something like that. Okay, how do you find out the minimum point? What u0 should choose if you want to minimize j?
Take the derivative, set equal to
Take
0.
the derivative, yes, and set it to 0, exactly. Okay, right. Does this notation mean that we are minimizing? Yes, we are minimizing over u0, u1, u2, right? So we want to choose the value of u0, u1, and u2 so that the j, which is the average, the square the discrepancy, is as small as possible, right? Okay, so here we want to take the derivative of j with respect to u0 and set it to 0. When we want to minimize a multidimensional function, we do the same, except for the derivative of j with respect to all the independent variables, all the things we can choose has to be 0. That's what we call a first-order optimality condition. It's a necessary but not sufficient condition for the function to be optimal, okay, to be minimized. So what that means is that we want to take the dj, du0, we want to set it to 0, we want to set dj, du1, set it to 0, and dj, du2, set it to 0, okay? All right, so before we can do that, we want to substitute the form of u, right? Well, we want to represent this u as a function of these three numbers. So let's figure out how to do that. And we're just doing this in this special case, and that actually generalizes later on into finite element method for solving differential equations. Okay, so let's figure this out first.